Greetings, trigonometry friends. Today we're going to be going over angle measure. This is from chapter 3.1 in the book. Now for angle measure, it's somewhat of a review, but not totally. We're going to be looking at it from a slightly different angle. We've got 3 points that define these lines here. We've got an A and an O, and then we've got our point B right there. And so note that that point O, that corresponds with the vertex of the angle, and that's usually located at the center of the unit circle for our purposes. And right here, this first one, we have a positive angle, and then the next one we're going to look at, that is going to be a negative angle. Alright, so positive because we're rotating in this direction here. And note a few things. We've got our initial radius 1, and that's being rotated up by an angle theta. This is again a positive direction to a new radius pointing in a different direction. And so we would call this the initial side. And then when doing the unit circle, we would usually refer to that line as the reference side, and that goes up to the terminal side. All right, and so we would call this angle AOB. All right, and then for the next one, for the negative angle, it's still kind of the same thing. We got our point A right here. There's our initial radius going out to the new radius. We have our points A, O, B being rotated negatively. And again, we've got our initial side and our terminal side. And we would call this angle AOB as well. Note that we start off with the point that's on the initial side, and then we end on the point that is on the terminal side. Alright, and so this next verbiage, we've gone over it before. Theta is a measure of the rotation. And an angle describes how far a line is rotated. So in degrees, one full rotation is 360 degrees, or 2 pi radians. And angles in a circle are measured from a reference side. Which correlates with the initial side of the angles that we just looked at. And so note that to go back and forth between radians and degrees and rotations, we simply note that 1/2 of a rotation equals 180 degrees, which equals pi radians. And so that will always be the tidbit we use to go back and forth. Now we're going to look a little bit more deeply into radians as far as how they're defined. This equation, as you may recall, is the arc length. S is the arc length. Right, so this would be our arc length right here. That's our S. And then, of course, we have our radius, which is going to be, here and here. And then we've got our theta, which we should be able to identify without me drawing it on there, but that of course would be this theta right there. Alright, so let's go ahead and rewrite this as theta equals S divided by R. And I want us to note what happens when the arc length is the same as the radius. Well, then the above equation becomes theta equals r divided by r which is 1 radian. And so in fact this is the definition of 1 radian. It is what happens when we are on the circle, and the arc length is the same as the radius. So when we look back at this picture here, note that the radius is the arc length. Right, these are all the same, so therefore this is 1 radian. And so each one of these guys you see in here represents another radian. So we go over, and that gets us down to 2 radians, right? Just 1 more radian. And then we've got another guy here that's 3 radians. And then we keep going to get to 4 radians, 5 radians, and then we have 6 radians. All right, so each one of those triangles that we went through is 1 radian, and note we've got not quite 1 full rotation at 6 radians. Right, we got a little bit more to go, but do note that these are pretty close, fairly close. It is a little bit off, but just for estimation purposes, 1 radian, that's not too far off from pi over 3. And that should kind of make sense. Pi is, a little bit more than 3, 3.14 with a whole lot of change. And so when you divide that by 3, you get a result that's pretty close to 1. A little bit more than 1, but it's pretty close. And so we can see 1 radian. It's not far off from that guy there. And then we have 2 radians. Well, that's pretty close to 2 pi over 3, right? 2 times pi, that's a little bit more than 6. Divide that by 3, not too far off from 2. Pi radians, again, that's a little bit more than 3. And so, which, makes sense because this isn't, quite halfway over. This guy is when it's at pi. The next guy we have on here is going to be 3 pi over 4. And then we've got, 4 pi over 3. And then we've got 5 pi over 3. All right, so each one divisible by 3. It should be pretty obvious why we're looking at those in this case. And then, of course, when you go all the way over, that would be 2 pi. It's 0 or 2 pi rotations. 2 pi, well, that's a little bit more than 6. Note 6 radians does not get us all the way around. We need those extra decimal places in the pi. We multiply it by 2 to get 1 full rotation. So you should have a pretty good intuition, of what 1 radian is in relation to the unit circle and in relation to some of the reference angles that we've been looking at. All right, so now let's go ahead and move on. We're going to look at linear and angular speeds. So we're going to go ahead and write this as, what an angular speed is. Well, that's going to be a, per time. This dot simply means whatever our angle is as a per time. And so it'll end up, typically we see radians per second, and we also see another one called rotations per minute, RPM. You'll see this a lot on engines. And so theta dot is a common notation, but commonly, and you also see the letter omega right there. So that's want to make sure you're aware of those. And this is very similar to when we look at how is our arc length changing. Right, that would be our speed along the edge, the tangential velocity, if you will. And so this is simply the arc length divided by time, like how long it takes you to travel that arc length would be what you're dividing by. And we write this with a simple letter v for velocity. All right, now let's look at our equation. S equals r theta, right? That is our arc length equation? Well, we want to know what is our per time, right? Our velocity, if you will. Well, that will just end up being the radius times theta dot, which again is which we can write with the notation used often in the book. The velocity is the radius times omega, where omega and theta dot are one and the same. Now, this equation is only valid if the radius is constant. That is, if your radius isn't changing. And since we're dealing with circles, the radius will be constant. But just note that if the radius were changing, we would need to modify this equation a little bit. All right, so let's go ahead and look at some examples on the back here. Okay, and this one, there will be a video in the module going over this example, but we're going to go ahead and work through this right here as well. The Greek mathematician Eratosthenes, who lived about 300 BC, measured the circumference of the earth from the following observations. He noticed that on a certain day, the sun shone directly down a deep well in Syene, which is in modern Aswan. So basically, certain time of day, sun, you could look down, you could see the reflection of the sun perfectly. And at the same time of day in Alexandria, which is 500 miles north, right, just in a straight line north, if it was east or west, this wouldn't be valid. The rays of the sun shone at an angle of 7.2 degrees to the zenith. Find the radius and circumference of the earth. All right, so by 300 BC, it was pretty well established that the Earth was a sphere, and so the big question was, what was the diameter of the Earth? So the way this is set up is that the first assumption, because it had to be an assumption back then, 300 BC and all, was that the sun was very far away, and this requirement of the sun being far away meant that all the sun rays came in parallel lines, right? Again, if we'll have the sun right here, of course, this is not drawn to scale since the sun is obviously much larger than the Earth, and at the scale I've drawn the surface of the planet over here. If I were to draw the sun on the same scale, it would be very, very far off the page. All right, so the way this is set up is first we've got our initial stick right here. All right, and that was the one that looks like it's the one that's in Syene. And then we've got the other stick that's in Alexandria down here, like so. So you can see that when these sunbeams come through, there's going to be no shadow here, right? That's when the light shining all the way down to the well. But when the sun comes, the same sunbeams are coming in. Sorry, I'm having trouble with getting this thing to draw. There it goes. It will create this shadow right there. And so what we want to observe here is that if you draw a line from the stick straight down here, draw from the stick straight down here, imaginary lines, you'll end up at the center of the Earth, which is, our radius. And this will create an angle theta right here. So let's kind of continue this line out. And so this angle theta will be here and then right there as well. And so the next bit is, the arc length. Well, this is 500 miles, right? That is our S. That's our distance right there. The way Eratosthenes was able to estimate that distance was that he had actually hired someone to walk the distance in between the two cities while counting their steps, which seems like an amazing feat in and of itself, particularly when you start looking at the accuracy that they were able to make this calculation with just using sticks and shadows. So let's go ahead and run through that. We've got our equation, S equals R theta. So note that we already know what S is, that's 500, and then we also know theta, which is 7.2 degrees. Now note we are going to have to convert theta into radians for this calculation, not a problem. And as a matter of fact, let's do that right now. Theta equals 7.2 degrees, but we don't want degrees, we want radians. So we convert this to radians by simply going 180 degrees in pi radians. And this gets us 0.1256. And that is again in radians. Okay, so we've got that number there. And so now we're going to set this up for the radius. So radius equals S divided by theta. And so this simple calculation becomes 500 miles divided by 0.1256 radians. And when you run through that calculation, you get 3,980 miles. So the equatorial radius of the Earth that we have on record is 3,949.9 miles. Which means that this calculation is within 1% of accuracy, which is quite astounding. Now, to calculate the circumference of the Earth, remember that's just a simple calculation based off what we already know, 2 pi r, and we know we're doing our own estimate, not the number that we recorded here. So that would be 2 pi times 3,980. Of course, the actual number's not going to be too far off. And then, which is about 25,000 miles. Okay. And you note that I'm not writing all the numbers out because we only have a two-digit significant figures here. So. So there we have it, 25,000 miles, and that is an astonishingly good estimate. If you have not done so already, go watch the video I have posted along with this about Eratosthenes with Carl Sagan. He gives a very in-depth picture of what's going on and a little bit more into the history. I think you guys will really enjoy that one, so make sure you do watch that. Okay, moving on. We have our next example. We have two gears. Gear 1 is 6 inches and gear 2 is 8 inches. So let's go ahead and draw that. We've got gear 1. And we'll just kind of put our little gear things on there. So we'll call that gear 1. And that again is 6 inches in diameter. And we'll say it's turning this direction. Then we've got our gear 2. I got a little gear things, gear 2. And this one must be turning this direction in order for them to match up. And again, that is 8 inches. Gear 1 is turning at 60 RPM. That would be rotations per minute. So I want us to note that both of these gears, regardless of the differences in radius or their RPMs, will have the exact same velocity at this point right there, at their edge. Because if they do not share the same velocity, there will be slippage among the gears, and you do not want that. You'll have a very poor functioning gears if you do have slippage. So you want those velocities to be the same. So our velocity if you'll look up, we already have the equation over here. It's the radius times the angular velocity. And that's going to be true of both of them. So since they both have the same velocity at that point, we'll just say the radius of gear 1, angular velocity of gear 1 equals the radius of the gear 2 times the angular velocity of the gear 2. And so let's go ahead and solve this for what we're looking for. We want to know what the angular speed of gear 2 is. And so W2 equals R1 times omega 1 divided by R2. Alright, so let's go ahead and identify each of these. Radius 1, well, that's going to be this guy here. The radius 2, well, that's this guy here. And then the angular speed of gear 1 is this guy right there. So putting all these together, we have 6 times 60 RPM, and that quotation mark simply means inches, and we divide that by 8 inches. All right. Run through this calculation and you will get, so this will get you 45 rotations per minute. And so we want this in terms of radians per second, so we need to do a quick conversion. So we have 45 rotations per minute. So in one rotation, we have 2 pi radians. Okay? And then in 1 minute, we have 60 seconds. So we go through that calculation and we get 4.7 radians per second. And there we have it. That is our angular speed of the second gear. Alright, so real quick, we're going to look at the area of a circular sector. So basically for this, again, it's the area of a section of a circle. Right, so say we're looking for, an area in there. And so to calculate this, we simply have the area of, whatever angle theta is right there, over 2 pi, right? Because that would be the fraction of the section, and we multiply that by the area of the circle that we normally would have. Okay, and so this, continue on with this. Theta divided by 2 pi times pi r squared. And so we have pi's cancel. And so we have theta, or we'll do it like the book has it, 1/2 times theta r squared. And there we have it. That is the equation for the area of a circular sector. And so we're going to go on and look at an example. An irrigation system pivots 280 degrees with a radius of 300 feet. How many square feet does the sprinkler irrigate? And again, you can find this problem on page 173 in your book. So 280 degrees, that's quite a bit of the area of the circle. Right, that's basically what's being watered here. Right, 280 degrees, that's our theta. All we got to do is just plug this into the our equation here. And so our radius was what, 300 feet? There's our circle, so we just go, okay, so the area of the sector equals this thing will write 1/2. Well, right now we've got it in degrees, so that's the one thing. Let's go ahead and just take care of that right now at the beginning so we don't have to do it later. We have 280 degrees, and then there are 180 degrees in pi radians, which will get us 14 pi divided by 9. Alright, so we put that in there. 14 pi divided by 9 multiplied by the radius of 300 feet. Run through the calculation and we get 219 thousand square feet. And you know, there are more digits in here, but we're going to go ahead and just round it to 3 for this calculation. All right. So that is that one. So now we move on to chapter 3.2 and 3.3. Just a little bit about right triangles. Again, sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is the opposite over the adjacent. And so, just to make sure we all have this picture, there's our theta, here's the adjacent, there's the opposite, and here is the hypotenuse. Alright, so we want to go ahead and find everything for this triangle here. So we're going to go ahead and run through that. It is a right triangle, as you can see, and we've got an angle right here of pi over 5. So when we do this, first let's go ahead and look at this side here. We'll call this side A, we'll call this side C, and let's call this angle beta. So to find angle beta first, we can go ahead and do that. Keep in mind, you know, the sum of the angles is going to be pi, right, 180 degrees. So we've got pi over 2 plus pi over 5 plus beta, and this all has to equal pi. So we want to go ahead and just do some basic arithmetic here. We got 5 pi over 10 over 2 pi over 10, so that's going to get us 7 pi over 10 when we bring them together, and then when we subtract, we'll get beta equals 3 pi over 10. Alright, so that's one of the numbers we're looking for. Let's go ahead and color code it. Alright, that one was easy. Now we got to get A and B. We're going to use our basic trig for that one. Let's see, so A is the adjacent side. And so we'll say cosine of pi over 5 equals sorry, let's not use cosine because that's just going to be A over C. Let's use sine. So that way we can actually figure out one of our unknowns. Sine, will, we have our opposite, which is 106. Divide that by C. So C equals 106 divided by sine of pi over 5. And so when you put this sine of pi over 5 in the calculator, you should get 0.5877. and then you perform the final calculation to get $180 and some change. We'll just cut it off right there. Truncate it. 180.3. So that's our C. Let's go ahead and color code that one. Now to find the final side, we just use good old Pythagorean's theorem. A squared plus B squared equals C squared. Like so. And then we simply solve. And we end up with this guy right here. And that will get you 145.85. And that is our final side. Color code that one. And there we go. So we just used some of our basic trig to find all the different sides of a triangle. Should be a bit of a review, but hopefully that does give you a good refresher. So let's go ahead and use this for a real-life example. We have a surveyor who is trying to determine the distance to an object, but he is unable to measure the distance directly. So basically, we're trying to come up with a calculation. We've got a surveyor. He's got his little instrument here where he's measuring distances. This measures angles is what that does, and so he's got the object over here that he's trying to find, and he wants to know, okay, what is the distance from here to here? So what he's going to do is he is going to have one of his guys stand with a rod that he can measure the angle from, and this will be a known distance off. We'll call this distance B. Right, here's this guy holding it so he can measure it. And so what they do is he'll measure, okay, how far off to the side is that? What angle? Theta. And so what you need to immediately recognize is that this is a right triangle. And we're trying to find D. B is known, right? Because the guy is going to the object. He's just kind of walking off a measured distance. And so we're going to use the tan function. So tan theta equals whatever distance that the rodman walked off to the side, because that is measurable, divided by the unknown distance. Solve for the distance, and we get distance equals B divided by tan theta, which is the same thing as B times cotangent theta. And there we go. That is the equation that a surveyor would use if he's trying to figure out the distance between two objects, but he can't measure them directly. There could be some kind of creek bed or some kind of obstacle that prevents him from doing a direct measurement. This is what he would do. All right, so we're going to go ahead and do a quick definition of the trigonometric functions. We just looked at one right there. We already know sine, cosine, and tangent. Cosecant theta. Well, that is, again, 1 over sine theta, which is the hypotenuse over the opposite. And then for the secant theta, again, just 1 over cosine. And I'm just going to use H to stand for the hypotenuse and A to stand for the adjacent. And then cotangent theta, well, that's just 1 over tangent theta, as we saw just in the above example. And so that gets us the adjacent divided by the opposite. Let's put a little line through it so you know that is not a 0. Right, that stands for opposite. All right, and so now for the Pythagorean identities. So this all starts off with r squared equals x squared plus y squared. And so we've already seen that sine theta equals y divided by the radius, and then cosine theta equals x divided by the radius, making this one r sine theta equals y, and this becomes r times cosine theta equals x. And so we simply make these substitutions into our equation for a circle. And we have the radius squared equals r squared times cosine squared theta plus r squared times sine squared theta. Note we can factor out an r squared on the right hand side, divide both sides by r squared, and we get 1 equals cosine squared theta plus sine squared theta. And this is, again, a very important trigonometric identity. I know we've touched on it before, but it's worth bringing up one more time. From this, we can get all the other trigonometric Pythagorean identities. If we divide this guy by cosine squared, dividing by cosine squared theta, we'll get secant squared theta equals 1 plus, and then we have sine squared over cosine squared, so that is tan squared theta. So that would be the other one. Or we can divide this guy by sine squared theta, and so that would get us cosecant squared theta equals cotangent squared theta plus 1. Okay, so those three are pretty important. It's important to know where they come from. They will come up time and time again. So a reference angle, basically, if you have, here's our x, y coordinates, and we have our angle in our standard position. Say it's coming over here, and so this is that angle theta. Well, the reference angle would be the angle that gives us an acute angle formed by the terminal side of theta. So in this case, that would be this angle right there. We call it with a little hat there. For each of the quadrants, of course, if you're in the first quadrant, your angle theta is the same as the reference angle. No surprise there. We covered quadrant 2. If we go into quadrant 3, right, here's our angle theta. Well, there your reference angle would be this guy right here. And then for quadrant 4, right there, kind of the reference number when we're dealing with the terminal length from a few chapters before. Now the area of a triangle, remember the equation. The area of a triangle is 1/2 the base times height. And that's what we're still going to be going off of. Of course, we need to figure out what is the base, what is the height. So say we have this triangle here, and we've got A and B here. We'll note that the height in this case would be that dashed line there. Here's our angle theta. So we need to figure out what the height is, what our h is. So h would be, now we use the sine function. Let me switch to red. We use the sine function, sine of theta, equals the opposite, which is the height, divided by the hypotenuse, which is b. Okay. And so again, we want to solve for the height. So height is simply b times sine theta. And note that the base, well, that's just going to be this length right there. So we have everything accounted for. So the area of a triangle becomes 1/2 our base, which is A, times our height, which is B sine theta. And you'd get the same result if you define the height based off of any other side as well. So that is the equation. And that is all we have for the day. I wish you guys a good day and good luck with the week.